to introduce Jacob Barandes, who is a philosopher of physics and a mathematical physicist at Harvard University. Jacob obtained his PhD from Harvard, where he is currently working. He has published extensively in both philosophy and scientific journals, philosophy journals such as Synthèse and the Foundations of Physics. He works on the history and philosophy of quantum mechanics, the foundations of theoretical physics, as well as relativity theory. And today he will be talking about on causal locality in a deflationary account of quantum theory.
It's back to 3 years ago, where everything was on Zoom.
Thanks so much. Can you all hear me okay? Is my audio coming in now? Can I just get a confirmation that you can all hear me? Thumbs up? Thumbs up, okay, yeah, good, okay. Thank you very much. All right, so I'm gonna get started. It's an ambitious talk, so let's get going. My talk is called On Causal Locality in a Deflationary Account of Quantum Theory. I will explain the Magritte painting in a moment. And the talk is connected with 3 papers. I have the archive and Phil-Sci versions all listed here. This is an outline of the talk. I'll start with an introduction. I'll talk about some problems with textbook quantum theory, some that are familiar and some that I believe are new. Then I'll talk about, I'll make a brief interlude on laws. We'll see why that's going to be really important for setting up the next part of the talk, this new formulation of quantum theory. Then I'll talk about how in this new formulation we can account for many of the exotic quantum phenomena that usually we associate with textbook quantum theory, but in a deflationary way. And then I'm going to turn to questions of causal locality in the last part of the talk, and then I'll conclude. So in most textbook treatments of quantum theory, one takes the basic object to be a wave function in Hilbert space, H, over the complex number C, axiomatically evolving according to the Schrodinger equation for some self-adjoint Hamiltonian H of t. Here's the Schrodinger equation. Sometimes one instead takes the basic object to be a density matrix, rho of t on the Hilbert space, or a map on a C-star algebra. But morally, it's roughly the same idea. Then there's a host of other axioms that provide an instrumentalist algorithm for using the wave function to calculate probabilities of measurement outcomes. And much of the interpretive debate lies within this wave function paradigm and asks about the nature of the wave function. Is it epistemic? Is it ontological? Is it nomological? Something else? And whether it should be supplemented with additional or hidden variables. This talk has 2 ambitious goals. The first is to review a new, axiomatically simpler, arguably empirically adequate, metaphysically deflationary formulation of quantum theory that lies outside the wave function paradigm that borrows heavily from some recent results in the literature that only go back 5 or 10 years. The next part of the talk, the next goal, is to challenge some of the conventional wisdom surrounding causal locality and hidden variables by arguing that this new formulation is, in fact, a causally local hidden variables theory. One larger lesson to take: when probing fundamental questions, it really helps to have a concrete model or theory in hand rather than just abstractly speculating. All right, some problems with textbook quantum theory. So there's the measurement problem, right? We're mostly familiar with the measurement problem. Activating the quantum theory's measurement outcome predictions requires saying poof at some point and magically invoking a measurement which the textbook axioms don't define. On the one hand, if one doesn't invoke the measurement axioms, then the textbook theory has no connection with physical reality, and the mathematical symbols you write on paper are no more physically real than Magritte's famous pipe, hence the first slide, or Alfred Krzyzewski's famous maps. Maps shouldn't be confused with the territory they represent. On the other hand, choosing to invoke the measurement axioms depends on making a subjective decision about when a measurement has happened, meaning that one outcome is supposed to be singled out for collapse of the wave function with in principle empirical consequences. See, for example, the Wigner's friend thought experiment. The Wigner's friend thought experiment, you have one experimenter, Wigner's friend, inside of a sealed box doing a quantum measurement. Wigner's on the outside, and the observer on the inside presumably gets collapse when they do the measurement, but Wigner on the outside doesn't see a collapse. And in principle, these actually make different predictions about what's supposed to go on. Anyway, this simple dilemma between these 2 hands, this is the measurement problem. But I would argue that the textbook axioms contain another profound problem, distinct from the measurement problem, and one I don't think has been named before. So on the one hand, scientists talk about various phenomena physically happening, perhaps probabilistically. Ornithologists talk about birds exhibiting foraging behavior. Early universe cosmologists talk about primordial gases mixing. Microbiologists talk about DNA replicating. These are all examples I've taken from conversations I've had with scientists. Now, often one works with statistical averages over such phenomena happening, as in classical statistical mechanics. We don't know exactly which trajectory a system takes, so we do some kind of average over possible trajectories to get some coarse-grained description of what's happening. For example, if one can assign probabilities to the possible trajectories of a particle undergoing Brownian motion in a fluid, then one can compute the statistical average over those trajectories and get like a bulk behavior. But still, bulk behavior phenomena really happening in the fluid. On the other hand, according to the textbook axioms, quantum theory is an instrumentalist recipe or prescription that narrowly predicts only measurement outcomes, measurement outcome probabilities, and expectation values that are defined as statistical averages of measurement outcomes weighted by measurement outcome probabilities. So the only outputs of the textbook theory are narrowly about measurement outcomes alone, not about general phenomena happening. Unless one changes the textbook axioms, there is just a conceptual gap between one category, phenomena happening, broadly speaking, and another, at best, subcategory, measurement outcomes, and it would be a category error to confuse these two things. I call this dilemma the category problem. In particular, it would be a category error to confuse happening averages of the kind that one sees in classical statistical mechanics. The system actually does something we're not exactly sure, so we do some averaging over the possibilities, with measurement outcome averages, quantum theoretic expectation values, which again are statistical averages of measurement outcomes weighted by measurement outcome probabilities. These are distinct things. In other words, just because these two quantities are often both written in brackets, and in some cases may have approximately the same numerical value for certain choices of the symbol x representing whatever it is that we're talking about, that doesn't mean that they're physically the same categorical kind of a thing. And yet this elision between these two quantities is implicit and pervasive in textbooks and the research literature, from condensed matter physics to quantum gravity. If you pick up one of the standard textbooks on quantum mechanics, Shankar's book, Principles of Quantum Mechanics, he has an entire chapter called The Classical Limit that is basically just this fallacious conflation, the whole chapter, where he just confuses these two kinds of averages. Quantum theoretic expectation values and related quantities like correlation functions and functional integrals, nonetheless, are often talked about as if they are averages of phenomena really happening. People often switch between talking them as measurement averages and measurements of phenomena happening, but the axioms don't license one to do that. Could we resolve the category problem by somehow taking the mathematical ingredients of textbook quantum theory and reifying them, making them real things so that what happens to them really is something really happening? Well, what ingredients are even available in the textbook theory? We've got the Hilbert spaces, or the complex numbers, state vectors, wave functions, density matrices, self-adjoint operators representing observables, time evolution operators, Hamiltonians. Now, one issue, of course, is that these are purely mathematical objects. Another problem is that they don't live in 3D space or even 4D space-time or anything even like it, not 10D space-time. But perhaps we can get around that by some kind of metaphysical move. We can think of them as maybe properties of things that live in space, or maybe we can get around this with some notion of patterns or emergence. A reason to be skeptical about assigning a physical meaning directly to the Hilbert space ingredients is that quantum theory contains a little-known form of gauge invariance. So if you let v of t be any time-dependent, and that's crucial, unitary operator, well, you can do the following transformation on the mathematical ingredients of the textbook theory. You can map all wave functions to wave functions multiplied by this v of t. Density matrices and observables get similarity transformed by v of t. Time evolution operators, you get what looks almost like a similarity transformation, but note because they connect what goes on at t equals 0 to later t, v dagger on the right-hand side is evaluated at 0. And if you actually work out what happens to the Hamiltonian, you get this very interesting transformation law that is mathematically identical to the transformation law of a non-abelian gauge potential in a gauge theory like quantum chromodynamics. This is actually not a surprise, because you can think of a quantum mechanical system as being like a Hilbert space fibered over a one-dimensional manifold that represents time. You can think of a copy of the Hilbert space stuck to each moment of time. And essentially what we're doing here is we're doing independent unitary rotations of each fiber. And the Hamiltonian plays the role of the connection for that fiber bundle. So this is actually a good reason for this. I should note that this overall transformation was first written down, as best I can tell in its general form, by Harvey Brown in a philosophy paper in 1999 on non-inertial reference frames in non-relativistic quantum mechanics. But this is very general. The last thing to note about this is that this transformation behavior of density matrices in particular does not commute with partial traces. Okay? And this is actually crucial because it means that there is not an unambiguous density matrix you can assign to every system. You know, people talk about, oh, we can't assign a state vector to a system if it's entangled, but we can assign it a reduced density matrix. Because of this transformation, which doesn't commute with partial traces, you can't even assign a unique reduced density matrix to every system. And that's actually, in my opinion, a pretty profound problem with trying to take the ingredients of the textbook theory seriously as physical things. So all these Hilbert space ingredients are gauge dependent. And so that transformation is a kind of gauge transformation in the previous slide. And so their physical meaning is therefore highly suspect. Indeed, you can map any state vector trajectory, take a wave function moving through a Hilbert space in some trajectory. With this V of t, you can actually map it to any other trajectory you want. And so a state vector trajectory doesn't actually contain any gauge invariant physical content. What is gauge invariant in textbook quantum theory? You could ask, in electromagnetism, what's gauge invariant, right? We have gauge potentials in electromagnetism as well. But in electromagnetism, we can package those gauge potentials, those gauge-dependent potentials, into gauge-invariant physical things like electric fields, magnetic fields. They have a very concrete physical interpretation. An electric field is at some location the force per unit charge experienced by some body with charge there. So the question is, could we package the gauge-dependent features of the textbook quantum theory into things that are gauge invariant? Well, the problem is the gauge invariant things are just measurement outcomes, measurement outcome probabilities, and their expectation values. But then we're back to talking only about instrumentalist quantities, and so we run right back into the category problem. All right, this is a good moment to take a brief interlude and talk about laws. So let's step back. Right? We want to find a version of a way to think about quantum theory in which stuff genuinely happens. Let's take a step back and try to devise the most general, non-instrumentalist, genuinely physical theory in which phenomena truly happen. Let's start with a list of possibly coarse-grained configurations. I'll denote them by Latin letters I, J, and so forth, forming a configuration space C, which could be infinite, could be a continuous configuration space. This is not going to be configuration space realism. I'm not saying the configuration space is the seat of reality. My configuration space is just a menu, a list of possible configurations. Now, C can often be coordinatized by degrees of freedom, where we identify each configuration by values of degrees of freedom, Q1, Q2, and so forth. These configurations are, for the physical theory, what gives it its ontology. We're saying these are the ways that the physical system can be. These are what its configurations can be. For each time t in some index set, capital script T, let pi of t denote an epistemic probability distribution over C. So at that time t, what pi of t does is it assigns some probability that that is the configuration that the system occupies at that time t. And as good probabilities, they're between 0 and 1, and they sum to 1 over I. Note, you can arrange these probabilities. If you take I as the index, you can arrange them as a column vector, P of t, where the entries of P of t are indexed by I. Just a note that will be useful later. Okay, well, so far this physical theory has an ontology. We've said it has some set of configurations, and that would depend on exactly what kind of system we want to model. We want to model fields, we'll pick field configurations. We want to model particles, we'll pick particle configurations. It's up to us. But there is not yet a nomology. I haven't specified any laws, right? And I'm going to use brown text for clarity to indicate when I'm talking about laws. That'll be important. If we could start physics over again from scratch, without the advantages, but also without the burdens of scientific history, could we imagine a more general set of laws than in existing theories? And this is going to be crucial. And by the way, I'm going to proceed in a way that is friendly to both primitivist and Humean accounts of laws, which I think is also ostensibly an advantage of this approach. Well, okay, stochastic laws, laws that involve probabilities, are more general than deterministic laws because they contain deterministic laws as a special case. So if we want to look for the most general kinds of laws, we're going to look first at stochastic laws. This is from the Greek stokos or stochastikos for aim or guess. The most familiar kind of physical theory with stochastic laws is the sort of stochastic process defined in standard textbooks. Let me say a little about that, okay? So this is the set of laws, the nomology for a textbook stochastic process. Not going to be what I do, but this is the background of what you find in the textbooks. For a textbook stochastic process, and when you talk to many people in philosophy, mathematics, and physics, this is often what they assume. You typically assume that your laws have an enormous amount of intricate structure, often assumed implicitly, but it's there. You assume there are first-order conditional probabilities. That is, conditional probability the system is in its ith configuration at t, given that it is in its j1st configuration at time t1. Second order conditional probabilities, where we condition on multiple two initial times, third order, and so forth. People assume that all of these exist, where I, J1, J2, et cetera, are all elements of the configuration space, and the times are in that index set of allowed times. You can use these laws to define contingent joint probabilities. So you can take the standalone probabilities, Pj1 at T1 at some time. You can multiply them by an appropriate conditional probability from the laws. That's why this is brown. And you get joint probabilities now. Note these joint probabilities contain contingent information that correspond to the precise instantiation of the system. So you instantiate the system, you get some contingent values of these standalone probabilities, and then from this you get joint probabilities, and you get them for third order and fourth order and so forth. We then have a Kolmogorov tower of self-consistency conditions, just for marginalization. If you take these second order joint probabilities and you sum or marginalize on either of the indices, you have to get back first order standalone probabilities. All of these higher order conditional probabilities and joint probabilities have to satisfy this detailed, intricate set of interconnected self-consistency conditions. So a textbook stochastic process actually has an incredibly complicated and intricate set of laws. I also want to call your attention to the fact that the times listed here are listed in chronologically increasing order. This is usually assumed for a textbook stochastic process. The latest time is t, and then the times can be ordered in decreasing, farther and farther into the past. Here's some special cases. The simplest case is called the Markov process. For a Markov process, we assume that all those conditional probabilities exist and satisfy all the self-consistency conditions. We just assume that they trivialize for the most part. All of them reduce to the first order case, right? So if you try to condition on multiple earlier configurations, that's a well-defined probability. It's just that it's numerically equal to the probability where you only conditioned on the latest time. The latest time, we say, screens off the earlier times. This radically simplifies things. Note you can take these first order conditional probabilities and arrange them into a matrix indexed with rows by I and columns by J. And that'll be useful for later. For a discrete time Markov chain, which is the simplest case, the index set for t is discrete times. So the system evolves in discrete steps, and every time you go from one step to the other, you basically multiply by this matrix of conditional probabilities. It's the simplest kind of Markov chain. But actually, you can also accommodate deterministic processes in this way as well. An nth order deterministic process, and let's say second order because that's the most familiar kind from Newtonian mechanics. A second order deterministic process, we have second order conditional probabilities. They exist. It's just they reduce to ones and zeros. So you want to know what the configuration of the system is at time t. You specify the configuration of the system at two prior times. For a continuous deterministic process, the delta t's are infinitesimal. And once you know the configuration of the system at two prior times, then you uniquely, with probability 1, get the configuration of the system at the next time, or you get 0 if it's not allowed. So even deterministic systems live within this framework. And even things like conservation laws can be cashed out as statements about collective values of these probabilities as sort of coarse-grained statements about deterministic processes. So this framework is big enough to accommodate everything we've seen so far. But here's a generalization that assumes far less structure, and remarkably first appeared in the research literature as late as 2016, right? Very recent. We just assume first-order conditional probabilities. That's it. That's all we put in the laws. We have I and J, possible configurations, and here T and T prime, the T prime I'm conditioning on and T at the final time. These come from index sets T and T prime that might not be the same. This is clearly a strict generalization of what we've been doing. It has far less structure. Without loss of generality, I will take 0. I'll call time 0 to be one of the things in that set T prime of conditioning times. For marginalization, we get this self-consistency condition. It's the only self-consistency conditions that we get. We don't get a full Kolmogorov tower of self-consistency conditions, so this is much less intricate. Importantly, this is a linear relationship, very important. Once these conditional probabilities in the laws have been specified, we have a linear relationship between contingent standalone probabilities at T prime and at T. That's it. Notice these laws do not involve any assumptions about T versus T prime. I haven't assumed any fundamental breaking of time reversal invariance. T could be bigger than T prime or less than T prime. I have not assumed the existence of higher order conditional probabilities at all. I will argue in this talk that all quantum systems are contained in this class of physical theories. And we couldn't see it before because basically no one had ever written this more general set of laws down. And I'll argue that indivisibility, an important property that I'll define later, but also various quantum theoretic phenomena like interference are generic features of such systems when we don't impose all those intricate nomological structures that you find in a textbook stochastic process, right? So this is, I would argue, a very remarkable statement. By simply taking the laws to be simpler, but still having a configuration space, still having configurations and a familiar notion of ontology, we can accommodate quantum theory. Here's a fictional dialogue about this between, let's say, Aristotle and Galileo. So Aristotle says to Galileo, what makes an object continue in constant rectilinear motion rather than come to rest? Galileo says to Aristotle, you've got it backward. Continuing in constant rectilinear motion is the simpler, more default behavior. The trajectory of such an object contains less information. It's a straight line. What requires an explanation is why an object should ever come to rest at all, and why it should come to rest in specific circumstances. By analogy, in seeing what I wrote on the previous slide, you might ask, well, what makes laws stochastic? What makes them generically, as I'll explain later, indivisible? But that's getting it backward. Stochasticity and indivisibility are actually the simpler, more default behavior. Those laws I wrote down that feature these things, that's actually the simpler case. So in a way, those very general, simple laws are like the constant rectilinear motion of laws. What requires an explanation is why those features should break down in some circumstances and why we should get a much more intricate set of laws like we do for textbook stochastic processes or for deterministic systems. All right, now I'm going to talk about this new formulation of quantum theory. Here are some key motivating questions. First, what ingredients can we find to provide a genuinely physical foundation for quantum theory in which phenomena truly happen? Why is quantum theory based on so many abstract and seemingly ad hoc axioms? The complex numbers, Hilbert spaces, linear unitary time evolution, the Born rule, and non-commutative algebras. Can we get rid of that magical poof that's at the center of the measurement problem? Why do the equations of quantum theory in some cases resemble those of classical statistical mechanics, like the Liouville equation, at least in some rough formal sense? Is quantum theory ultimately causally local or not? And is there a connection between stochastic processes on the one hand and quantum theory on the other hand, which both involve probabilities, vectors, and matrices? I will answer all these questions in this talk. And I'll do that by presenting a new formulation of quantum theory in terms of a correspondence, a precise correspondence with stochastic processes. Why wasn't this formulation discovered before? Well, possibly, like I said, because it depends on some recently developed concepts that were unavailable in the 1920s and some that were still not widely known even by the 2000s. For one, stochastic matrices, right? These were introduced by Markov already in 1906, but they were not widely used until starting in the 1950s. This is decades after quantum theory was codified in Dirac's book in 1930 and von Neumann's treatise in 1932. And here I have a Google Ngram viewer to give you a sense of how, of when stochastic matrices became widely used. A special kind of stochastic matrix is called a unistochastic matrix. This was introduced only as late as 1954 in a paper on the real analysis of matrices by Alfred Horn, mathematician, and they were given their modern name as late as 1989. And finally, indivisible processes. These will be crucial also. These showed up in the research literature as late as 2006. And they're a distinct way to generalize Markov processes. In fact, the general process that I wrote on that earlier slide, the much less intricate process, that's in general going to be an indivisible process, and it's a different way to generalize being Markovian. So what's the path ahead? All right, here's the pithy one-liner, the takeaway, the picture to always keep in mind as this talk progresses. What I'm saying is that each system, perhaps even the universe, is in some configuration evolving along a trajectory governed or describable by stochastic laws. That's it. That's the picture. Now, to be more precise, unistochastic laws, I'll define what I mean by that in a moment, but for now, just note that outside the deterministic case, unistochastic will always imply indivisibility, and again, I'll explain what that means and how that's connected with various quantum theoretic phenomena. The path ahead, we're just going to construct the usual Hilbert space formulation with some definitions, identities, and theorems. It's just going to be math. I'm not going to need to reify or augment any of the Hilbert space ingredients or argue for speculative metaphysical hypotheses, and this talk should make you feel a little bit guilty about some of the traditional ways we sometimes talk about quantum theory. Okay. All right, so I'm going to start just with an analogy. This is the Hamiltonian formulation of a classical system. Right? Classical Hamiltonian formulation. We have, at the level of kinematics, the system has some configuration I in some list 1 through n in some configuration space C. Usually we assume continuous configuration spaces, so n will be infinite. This will be a continuously infinite set, and we really shouldn't be using a discrete index at all, but whatever. Generally, we'll coordinatize C with degrees of freedom Q1 through Qn. The dynamics consist of deterministic microphysical laws based on second order in time differential equations. Okay? Second order in time, that's going to be a second order deterministic system. We then write down the Lagrangian formulation, we write down the Hamiltonian formulation, and we work in phase space. We take our degrees of freedom Q1 through Qn, we add on the momenta P1 through Pn. Why do we do this? We do it because the differential equations are second order in time, and this lets us write the differential equations as first order equations. Hamilton's equations of motion for Q and P, where the dots are time derivatives. So we boil down the dynamics to 2n, double the number of equations of motion, but they're now first order. And if you treat the system statistically, you get the Liouville equation, where rho is a probability distribution on the QP phase space. Here, these brackets are Poisson brackets. This is the standard story you'll pick up in a textbook. Okay, so what am I saying quantum theory is all about? This is what I'm saying it's all about. These are the axioms. Level of kinematics, the system has a configuration, I, in some list, just like in the classical case. At the level of dynamics, now I'm going to help myself to this more general framework of laws. The laws are going to consist of stochastic microphysical conditional or transition probabilities, P of I at t, given j at 0. This is the conditional probability for the system to occupy its ith configuration at any time t, given that it occupies its jth configuration at the initial time 0. T here is, for our purposes, generally going to be variable. T, it can be smoothly varied. I guess depends on the theory. In some theories you want it to be discrete, in other theories you let it be smoothly variable. I'm not assuming it is bigger than or less than 0. And this generalizes deterministic equations and equations of motion. The second of the theorems listed on the cover slide contains a new theorem that shows that remarkably this is enough to give us quantum theory. I should point out this approach is not connected with the stochastic formulations of Bopp, Feniers, and Nelson from the 40s to the 60s. Nelson's stochastic mechanics is the most widely known. Okay, well, the standard rules of probability theory, this is just marginalization, imply that the standalone probability distribution Pi at t and Pj at 0 are related by this linear equation. I'd written this down earlier. This was that one set of self-consistency equations. I can write this more succinctly in this way by moving the i's and j's into indices and taking the microphysical stochastic probabilities and writing them as an array labeled by I and j, the final and initial configurations in t. Or even more succinctly in terms of matrices, using column vectors for the initial and final standalone probability distributions and capital gamma for that matrix of microphysical conditional probabilities. I'm going to show that the famous linearity of time evolution in quantum theory is not an accident, not an abstract postulate, but ultimately descends from this basic linear relationship. So we actually get an explanation for why the time evolution of quantum mechanics is linear. And that's, in my opinion, a major form of progress. Let's talk about gamma. Okay, so this n by n transition matrix, gamma I j of t, its entries are those conditional probabilities here. These are its entries. Indexed rows are I, columns are labeled by j. Well, it's got non-negative entries, and its columns sum to 1, because each column is, in particular, a probability distribution. So, in mathematical terms, we call it a column stochastic matrix. I will not be assuming that it is divisible, and now I'm going to explain what that means. So divisibility was a term introduced as late as 2006 for quantum channels. But then in a classical context, like the context we're using it in, talking about classical looking conditional probabilities, was only introduced as late as 2016 by several different authors. I'm not sure whether this was independent. I'm actually talking with these authors about where they got the idea. Okay, so what do I mean by indivisible? Generically, one has a failure of factorization across intermediate times. What do I mean here? The theory supplies us with gamma of t prime. That evolves from 0 to t prime. The theory also supplies us with gamma of t that evolves us from 0 to t. The question is there some intermediate stochastic matrix, gamma of t from t prime, that we can insert into this formula to give us an equality? That is, can we evolve from 0 to t prime and then multiply by some stochastic matrix that takes us from t prime to t and get the same answer as if we had evolved directly to 0 to t? If that's possible, we say our dynamics is divisible, but in general, it will not be possible. This gamma will not exist. There will not exist a properly defined column stochastic matrix with non-negative entries that will make this true. So generically, this will fail. We will not be able to pick any time t prime we want, stop the evolution, and our theory will not be able to supply us with a conditional probability to take us to the next state. Okay? So that in general is a feature of these general stochastic laws that I wrote down. They will fail to have this divisibility property. They will be indivisible. One says the gamma of T is indivisible and the system is a generalized stochastic system. So there's a theorem, and again, it's proved in that second paper, that by slightly enlarging the configuration space if needed, and by slightly enlarging, I mean you just basically add an extra degree of freedom if necessary, you can always assume that this matrix gamma of T is unistochastic. What does unistochastic mean? It means that each entry is equal individually, one by one, to the mod squared of the corresponding entry of an n by n unitary matrix. Okay? These mod squares are entry-wise. That is, we take each entry of U, mod square it, absolute value square it, and that becomes the entry of gamma. This is not matrix multiplication, and in particular, this rule does not commute with matrix multiplication. It's a little funny. The second thing to point out is this theorem requires the complex numbers. And this gives a very satisfying first reason why you want the complex numbers in quantum theory. Without the complex numbers, there's simply some generalized stochastic systems that you cannot write in a Hilbert space formalism. Allowing yourself the complex numbers lets you write all of them in a Hilbert space formalism. So here U is a unitary matrix. It'll ultimately be my time evolution operator. We call the system then a unistochastic system. That's what a unistochastic system is. And you can show now that a quantum system can be regarded as a unistochastic system in disguise. A system evolving on a configuration space along some trajectory stochastically according to laws given by gamma, where the entries of gamma are the mod squares of the entries of a unitary. So this new unistochastic formulation of quantum theory is going to deflate a lot of the exotic talk about quantum systems. Superposition isn't going to be literal, interference, decoherence, and entanglement are all going to have prosaic meanings now, and the measurement problem arguably dissolves. I'm going to say a little bit more about the complex numbers because I think this is interesting. So again, for n bigger than 2, an n by n unistochastic matrix will not generally be orthostochastic. You can't do it with just a real orthogonal matrix. You need the complex numbers to make it work. Hence, to exploit the stochastic quantum theorem and unitary evolution, the complex numbers or an algebraic construct isomorphic to them will be necessary. But from our point of view, Hilbert spaces are fictitious anyway, right? We just introduce them to make the math easier. And the complex numbers let us invoke all kinds of useful things. The spectral theorem, symmetry generators, Hamiltonians, energy eigenvalues, stationary states, the Schrodinger equation, the uncertainty principle. There's all kinds of things that we can do once we choose the complex numbers, so we might as well help ourselves to them. But they're not present at the level of the original system. The original stochastic system didn't have any notion of complex numbers. But actually, I think it's useful to point out that you actually also, to handle time reversal transformations are anti-unitary. They entail this operator called the complex conjugation operator K. It's an involution. You act twice with K, complex conjugation, you get the identity. That's K squared is 1. K anti-commutes with the imaginary unit I. It doesn't commute with I. And if you take I, K, and IK, what you find is they generate a Clifford algebra called the pseudoquaternions. And for more on the pseudoquaternions, you can look at this paper, this very interesting paper on complex numbers and quantum theory by Ernst Stuckelberg from 1960. So in a sense, quantum theory is really based on the pseudoquaternions, if you will, and not the complex numbers alone. Okay, so to reformulate the unistochastic process of quantum system, we're going to start by defining the system's density matrix. We take the initial standalone probability distribution, we sandwich it between U and U dagger at T, and this defines a time-evolving density matrix, rho of T. Now, this linear formula, and the reason why this is going to work, ultimately descends from that linear relation I wrote earlier, the linear relationship between the standalone probabilities at 0 and the standalone probabilities at T that I argued came right from classical marginalization. So assuming sufficient smoothness in time that you can apply Stone's theorem, I guess for some systems you won't get this, in other systems time will be smooth enough where you can avail yourself of this. You can go ahead and define the system's Hamiltonian. This is the standard definition of the Hamiltonian as the generator of infinitesimal time evolution. And then the density matrix will evolve according to the von Neumann equation. This is the standard von Neumann equation. IH bar d rho dt is the commutator of H with rho. Note, this is an actual commutator here because these are n by n matrices. This is not a Poisson bracket. I'm not making some hand-wavy analogy to statistical mechanics. That said, this does look a lot like the Liouville equation from the time evolution of the phase space probability distribution of a classical Hamiltonian theory. And actually, there's a good reason for it because this is playing an analogous role. This is describing the evolution of a sort of probability distribution over a configuration space. So there's actually a good reason why these look similar. If the density matrix is rank 1, then by definition, we can factorize it in terms of an n by 1 state vector in itself as an outer product of that state vector with itself. So rho of T we can write as ket psi bra psi, or equivalently psi psi dagger. The state vector then satisfies the Schrodinger equation. Right? Automatically, you get the Schrodinger equation out, which is remarkable. The Schrodinger equation emerges from what is ultimately just a stochastic process. So wave functions of the Schrodinger equation are, from this standpoint, secondary pieces of derived mathematics. They're not primary ontological furniture. We therefore see that wave functions are not purely epistemic, but they encode a blend of epistemic and nomological information. That said, they're not physical or ontological objects, and the standard unitary Hilbert space formalism yields a kind of divisible first-order differential equation. I mean, we ultimately got a first-order differential equation. It looks almost deterministic for the dynamics. So the Hilbert space picture is a way to sort of have your cake and eat it too, make it look like the dynamics is deterministic and first order, even though it's ultimately based on laws that are not. So we arrive at a stochastic quantum correspondence, according to which the Hilbert space formalism serves as a kind of analytical mechanics for stochastic systems, giving rise to an effective first-order differential equation, the Schrodinger equation. I should note this correspondence is many to one in both directions. A given generalized stochastic system may have many different Hilbert space representations, and a single Hilbert space representation may represent many different generalized stochastic systems. This isn't a surprise. This is just like in classical mechanics. You know, given a classical mechanical system based on second-order differential equations like Newtonian mechanics, like a Newtonian system, there will be many different many different Hamiltonian phase space representations, among other things related by canonical transformations. And a given Hamiltonian phase space representation may describe many different Newtonian systems. Like any form of analytical mechanics, like the classical Hamiltonian formulation, the Hilbert space formulation for a stochastic system provides a powerful set of mathematical tools for specifying microphysical laws in a systematic manner, for studying dynamical symmetries, and for calculating predictions. So it's very useful. But I would argue nothing more than a very useful software layer. Now let me show how I can account for those exotic quantum phenomena: interference, decoherence, entanglement measurements. So this new formulation is not limited to any specific kind of quantum system, but a well-known single particle thought experiment will provide a good example of how we account for the exotic phenomenon of quantum theory. So recall the double slit experiment. One imagines sending particles one at a time, it's always very important and emphasized, toward a wall with two slits and then observing where the particle arrives on the screen. Why one at a time? Well, usually you'll hear people say we do it one at a time so that you won't think maybe the particles are bumping into each other, but that's not the reason. Maybe it's part of the reason, but the bigger reason is that when you send them one particle at a time, the configuration space of the particle is 3D. That makes it easy to confuse with physical 3D space. And so you're teaching this to students and they're learning quantum mechanics the first time. You say, look, it's waves in 3D space. But really, all of this is happening in configuration space. And the fact that it looks like 3D space is just an accident of working with one particle at a time. Okay? If you'd sent more than one particle at a time, you'd need 3 n-dimensional configuration space. And then most students would say, hey, that's not actually very intuitive. But that's the truth. All right, so here is the setup. We have two slits close together. Let A, broadly speaking, denote starting conditions. I'm going to use a convention where, I'm going to continue on a convention where blue represents initial conditions, red final conditions, so C is where it lands. And I'll use purple for sort of any intermediate information, in this case, which slit the particle goes through. Okay, the usual assumption that's made implicitly when this is treated either deterministically or treated stochastically is the following relationship: that the overall conditional probability, initial conditions, that's what we're conditioning on, final landing site, is decomposable in this way as this summation, where we have conditional probabilities from initial conditions to which hole it goes through, multiplied by the conditional probabilities for which hole it goes through to landing site. This is implicit in all treatments, all classical versions of this story. And if the system is based on deterministic equations, then indeed this holds, because deterministic equations do have this feature. But this is implicitly assumed. But note, this doesn't follow from the general rules for how you marginalize, right? This requires a special assumption, a Markov divisibility assumption at B. Nonetheless, if you make this assumption, you get the following prediction. It's a histogram over many repetitions. You send lots and lots of particles through, and they build up the following histogram. They add together, you get this blend of distributions. And this matches observations from macroscopic particles like stones. Okay? So indeed, this is what you'd see if you were throwing stones at the wall. For an electron or photon, one instead observes what looks like an interference pattern. Okay? Does this mean the particle is really a Schrodinger wave, or the particle somehow goes through both slits? No, not necessarily. We'll show that one can account for this pattern merely by allowing the dynamics to be non-Markovian or indivisible. Remember, our general laws do not entail that this is true. Okay? And in particular, I'm going to show the discrepancy between them is exactly what interference is. Okay. So we have unistochastic laws. We can encode them as the unitary time evolution operator in the Hilbert space formalism. Given the unitary operator that takes you from 0 to t prime and the unitary operator that takes you from 0 to t, I can put them together in this way: u of t times u of t dagger prime. and define this purple matrix, this relative time evolution operator, that when you plug it back into this equation, in fact gives you what looks like a divisible story. You evolve from 0 to t prime. There is a well-defined unitary operator that takes you from t prime to t. And the result is this overall time evolution from 0 to t. Okay? That looks divisible, but remember by construction that the actual laws, the actual underlying microphysical stochastic conditional probabilities are given by mod squaring the individual entries of these matrices. And so if you attempt to take that relative time evolution operator and square its individual entries, that will give you a column stochastic matrix, but it will fail to be divisible. This difference will fail to be 0. This purple matrix you've introduced, despite being column stochastic matrix, will fail to equal gamma of t when you multiply by gamma t prime. There will be a discrepancy between this sort of naive closest divisible version of the process and the actual process. And when you subtract the two, you get exactly the formula for interference. And in the paper, I showed that formula. So you don't need waves or Schrodinger waves or anything like that. The exact formula for interference just comes from the breakdown between the actual dynamics not necessarily being divisible, being of this more general kind, and the nearest sort of divisible or Markovian approximation. And that's one way to understand what interference is. And arguably, anytime you have a breakdown between a Markov assumption and a non-Markov assumption, where the system is ultimately not Markovian, and you get different predictions, arguably we should think of all of that as a kind of interference, whether we're talking about quantum mechanics or something else. Okay, so I'm not going to have time in this talk to derive the whole story of observables and measurements and everything like that. I'm going to give just a brief sketch here. The details are in the paper. But borrowing language from John Bell, beables are the features of the system as they truly are, the way the system really is, the way it can be, versus the things we merely observe. In this formalism, beables are just random variables on the configuration space. A beable is a set of magnitudes. Given the configuration I, which could be 1 through n of the configuration, given the time t, a beable has some specific numerical value, right? If I take those numerical values and I arrange them into a diagonal matrix, I get a matrix A of t. And I can compute the probability, the expectation value the system will have one of those values. And given that I've written it as this diagonal matrix, the formula for computing those expectation values is exactly the standard formula for what you'd use in quantum mechanics. Okay? But in particular, this is a happening average. It's an average of the system truly having some configuration. It's not just a statement about measurements. If it happens that the diagonal matrix in question has just a 1 in one of its diagonal entries and zeros everywhere else, that is, it's an elementary projector, and if our density matrix happens to be rank 1, so it's factorizable as a state vector, then you obtain the standard Born rule. The probability of the system to be in its ith configuration to t is the absolute value squared of the ith component of the wave function. This is the original Born rule. By modeling the measurement process as an overall unistochastic process, one sees patterns of the dynamics. Again, this is all discussed in the paper, right? You just take the whole system, take the measuring device, treat it like any other. It's not treated as some abstract, axiomatically different system. You just consider a bigger system that contains a measuring device with its own configurations, and you have some overall stochastic process for the whole thing. What you find is that patterns show up in the dynamics that make it that look just like to the measuring device, like it has arrived at a definite result. And if you compute the probability with which the measuring device stochastically ends up in one of its measurement reading results, you get that probability is given exactly by the Born rule. So in some cases, the measuring device is measuring one of these beables. It's measuring an actual property of the system at some time. And so the reading it gets is really reflecting what the system's configuration is. In that case, we say it's measuring a beable. But you can take the same stochastic dynamics, you can just slightly tweak it. And now the measuring device can get readings on things that are not beables, on truly emergent patterns in the overall stochastic dynamics. To the measuring device, these look just like beables. The measuring device arrives at a result. It gets the result with some stochastic probability given by an appropriate form of the Born rule. But the thing it's measuring is not reflecting some simple property of the system, but sort of an emergent pattern. If you take the beables and all these emergibles, those emergent patterns that show up on measuring devices just like beables do, then collectively you get a non-commutative algebra of observables. You get the full non-commutative algebra, and therefore you get all the observables. That's where the observables are the beables together with the emergibles. And now we're done. We now have the complete textbook axioms. We've got unitary time evolution, we've got Hilbert spaces, we've got non-commutative algebra of observables, we have the probabilities, expectation values. We're done. We basically reconstructed quantum theory. Importantly, one can show that whenever an external system, like a measuring device or the environment, modeled as a perfectly ordinary stochastic system with some overall stochastic process over the whole thing, When it gets a reading of the configuration of a given subject system, you can show that once you marginalize classical marginalization, all at the level of the stochastic process, not a partial trace, just classical marginalization, when you marginalize over everything but the subject system, what you find is that the subject system spontaneously develops a division event. Spontaneously, this purple matrix shows up if the reading time was at t prime, the time at which the configuration of the system was read in by the other system. And then at t prime, we do get division, okay? And you can also show that at that time t prime, the density matrix for the subject system momentarily diagonalizes. So this reading of the system's configuration, this appearance of a division event when you can stop and now have laws for what happens next, this is exactly on the stochastic side what we would call decoherence on the quantum side. If t prime is indeed a division event, well, now our unistochastic system does in fact contain these valid microphysical conditional probabilities of this form. And for a noisy environment, a big macroscopic system in contact with a noisy environment that's constantly eavesdropping on some characteristic timescale delta t, you will inevitably get a Markov process, a process where you can in fact divide at almost every time t, and the process, you could write down the probabilities by concatenating these first order probabilities, and then we get what looks like a Markov process. This gives a very satisfying explanation for why so many phenomenological macroscopic systems are well approximated as Markov processes. All right, so now the meat of this talk, the final part of the talk, causal locality. Okay, so there's a case to be made that causal talk is just folk science, and I think I see John there. John, that's for you. And that's a perfectly, in my opinion, defensible position, right? That causation is not truly in the laws of nature. It's not truly fundamental. It's just a very convenient way of talking about science, especially when we talk about the special sciences. In that case, asking whether quantum theory is fundamentally causally local is arguably either unimportant or maybe meaningless if you're asking truly fundamentally whether it's causally local. But let's address those who take causal locality seriously in some manner, and along the way show how to make quantum theory a hospitable domain for talk of causal influences. So again, I'm borrowing a little here from John's language when John talks about, for example, certain circumstances providing hospitable domains for probabilistic talk and others not. I'm going to argue that there's a way to think about quantum theory, the way I've been describing it, that makes quantum theory potentially a hospitable domain for causal talk. Let's start with a simple first stab at a definition of causal locality. Causal influences cannot propagate faster than light. Okay, that's our first stab at this. Notice this is a condition on any causal influences that happen to occur in the system. Okay, we're not asserting that there must be certain causal influences out there. We're just saying that if your system happens to have any causal influences, then they must respect the speed of light. And here I'm borrowing a distinction that Wayne Mervold has been making clear recently. In a 1935 paper, very famous paper, and I like to put the in there, though it's not the title, can the quantum mechanical description of physical reality be considered complete? Einstein, Podolsky, and Rosen famously used an early version of quantum steering, language introduced that same year by Schrödinger, steering. In simplified form, you have two particles prepared in an entangled wave function, then separated in space. And then it happens that a measurement of one particle in a chosen basis can mean that the other particle's wave function collapses to a corresponding basis. And if you imagine changing which basis you measure the first particle in, there is an associated change in which basis the other particle collapses to. So the first observer can seemingly steer the other particle to a chosen collapse basis, again in language introduced shortly thereafter by Schrödinger. However, there's a theorem, the no communication theorem, that prohibits the first observer from controlling which specific wave function in that basis the other observer gets. So the first observer can't control exactly which wave function the second observer gets, but does seem in some weird sense to have some association between the basis in which the first observer measures and the basis the second observer collapses to. Einstein, Podolsky, and Rosen took for granted that the first observer couldn't actually have any influence on the other particle. But it's important to note, and they noted this, some quantum steered wave functions are eigenstates of certain observables. So if the first observer steers seemingly the second particle, they can steer the second particle to eigenstates of certain observables. Eigenstates, the eigenstate eigenvalue link says that if you're in an eigenstate of a certain observable, then your system's supposed to have a definite value of that observable. So EPR argued that their other particle must already have predetermined values of those observables. If you can steer the particle to a definite momentum eigenstate, the particle must have always had that momentum. If you could steer the particle to a definite position state, the particle must have always had that position, right? And so it seemingly has all those properties at once, and these are not captured by the original two-particle wave function, hence the author's conclusion that quantum theory is incomplete. Now, one could attempt to read the EPR argument instead, as implying that the first observer's measurement intervention non-locally causes the other particle to collapse to its final wave function. This would be a concrete manifestation of what Einstein later in a 1947 letter called spooky action at a distance. This reading, however, is contestable because it relies on a couple of questionable notions. One is wave function collapse, and the second is an interventionist conception of causation, right? The idea that causation is spelled out in an abstract agent intervenes on one thing and causes a change in some other variable. Interventions are almost inevitable if you're trying to use textbook quantum theory, because they're the only way you can get any experimental output from the theory is by doing measurements. And the theory, textbook quantum mechanics, treats measurements as axiomatic primitives. So you're kind of limited almost in a sense to this. But today we don't think of interventions as necessarily physically fundamental things. I mean, an intervener, an agent, Alice or Bob or whoever's doing the experiment, they're made of atoms. We don't think that the intervener or the intervention is like a fundamental physical postulate. In 1964, Bell was inspired by the EP argument and an existing non-local hidden variables theory, the de Broglie-Bohm pilot wave theory of Bohm mechanics. And again, this is that lesson why it's very useful to have a concrete theory in mind, because it can help clarify your thinking about things. He had a concrete theory in mind, Bohmian mechanics. He was motivated to write a paper called On the Einstein-Podolsky-Rosen Paradox, attempting to tackle the question of non-local causation head-on. Bell viewed the EP argument as creating a logical fork. Either accept causal non-locality or provide hidden variables that uniquely predetermine specific measurement outcomes, one or the other. To that end, Bell considered measurement deterministic hidden variables theories in which hidden variables did in fact dictate specific measurement outcomes, as in Bohmian mechanics. Essentially what Bell's trying to do is say, well, if you pick between causal non-locality or these hidden variables that uniquely predetermine specific measurement outcomes, let's see if doing that second part of the fork lets us escape causal non-locality or not. Okay. Bell's goal was to show that the second prong of the fork was in fact false hope. It could not ultimately save causal locality. Here was the setup. Bell introduced hidden variables lambda. A and B are the far separated measurement outcomes, and he assumed in this paper that they take on bivalent values plus or minus 1, and little a and little b are local measurement settings. Little a local to big A, and little b local to big B. Bell made the following assumption. This was his local causation assumption, that the measurement result for A did not depend on little b, and the measurement result for B did not depend on little a, but they could depend on the hidden variables. He assumed the hidden variables were variables, the kinds of things that could appear in functional dependence of this kind. There's also an implicit assumption in this paper of an interventionist conception of causation, but we'll see later how Bell deals with that. To Bell, these assumptions apply the following expression for the statistical average or expectation value of pairwise products A times B of measurement outcomes. So we have the following expectation value of the products of A and B. You multiply A times B in a given run of the experiment, and you average over the experiments, assuming some probability distribution for lambda. So here rho of lambda is some standalone probability distribution for the hidden variables, assuming they're variables, and assuming this probability distribution exists itself. That's a big assumption. Crucially, there's this important factorization that shows up here in this formula. That is crucial for getting Bell's theorem off the ground, and we'll see how important it is in a moment. It's ironic that Bell's results hinge so sensitively on assumptions about expectation values, because earlier Bell had identified a flaw in a much older 1932 anti-hidden variables theorem of von Neumann. Von Neumann had argued that you couldn't have hidden variables, but von Neumann's theorem relied on certain assumptions about expectation values that were unjustified. Interestingly, Greta Herrmann actually got there first in the 1930s. As far as I know, Bell did not know about her argument, but she pointed to the same flaw in von Neumann's proof. So getting your assumptions about expectation values right really matters. And Bell needed his expectation values to be of this form with that factorization in order to give his theorem. Using this formula for expectation values, Bell was able to prove his famous Bell inequality, which should then be satisfied by all measurement deterministic hidden variables theories. This is the Bell inequality. Quantum theory famously predicts violations of the Bell inequality, and indeed, the 2022 Nobel Prize in Physics was awarded to Aspect, Clauser, and Zeilinger for experimentally confirming those violations. So Bell's 1964 paper therefore appears to rule out locally causal measurement deterministic hidden variables theories. That second prong of the fork, measurement determined hidden variables, does not let you save local causality. Now, provided one doesn't take the EP argument to be definitive, Bell's 1964 argument leaves open several possibilities. Non-locally causal measurement deterministic hidden variables theories like Bohmian mechanics, measurement stochastic hidden variables theories where you have extra variables or variables in addition to or instead of the wave function in which you still have stochasticity, things are not uniquely determined, as well as formulations of quantum theory that at least attempt to eschew hidden variables completely, and that includes textbook quantum theory. Bell's 1964 argument certainly doesn't rule out hidden variables altogether. In 1975, Bell attempted to generalize his 1964 theorem to encompass the second and third possibilities, including the textbook theory, and implicitly to avoid relying on interventionism at all. So his new argument, 1975, applied to all theories with stochastic measurement outcomes, with or without hidden variables, so that includes the textbook theory, and arguably does not require an interventionist conception of causation. His goal was to show that all empirically adequate such theories, any theory empirically equivalent to quantum theory and empirically adequate, had to involve non-local causation. One big problem was in this more general picture, how to establish causation when measurement outcomes are stochastic, so there's no tight linkages anymore between doing something here and doing it there. But another was how to calculate the needed expectation value, because if you take these general assumptions, you don't get a factorization showing up in this formula anymore, right? You end up with this formula here to compute the expectation values. Without that factorization, you cannot derive the Bell inequality, okay? So this is a little bit like confusing. What do you do? Bell also wanted to introduce a concept of local beables, and I talked about beables before. Here's Bell's explanation of what he meant by beables. The beables of the theory are those entities in it which are at least tentatively be taken seriously as corresponding to something real. Local beables are the ones which are definitely associated with particular spacetime regions. In particular, Bell replaces abstract measurement outcomes with local beables also. He treats all these things as local beables, and you can read this as a way to avoid the need for treating measurement outcomes as abstract interventions, so you don't need to think in terms of interventionist conception of causation. But Bell pointed to another big problem, right? A more serious, so he points here that we're frustrated with the vagueness of quantum theory. You'll hunt in vain for where are the local beables. You'll find observables, but not beables. We'll have to do the best we can with these rather ill-defined local beables, while hoping always for a more serious reformulation of quantum mechanics, where the local beables are explicit and mathematical rather than implicit and vague. And one of the goals of my talk, the whole first part of this talk, was to lay out such a reformulation. So recounting his 1975 theorem years later, in a 1990 lecture, that same 1990 lecture, Bell says he starts with the following first attempt at a principle of local causality. The direct causes and effects of events are nearby, and even the indirect causes and effects are no further away than permitted by the velocity of light. This is very similar to that very simple definition of causal locality from the beginning of the talk. But then Bell goes on to say, the above principle of local causality is not yet sufficiently sharp and clean for mathematics. Just before he states his second attempted principle of local causality, he includes the following very important warning. Now, it is precisely in cleaning up intuitive ideas for mathematics that one is likely to throw out the baby with the bathwater. So the next step should be viewed with the utmost suspicion. He warned us. Here is his setup for his 1975 theorem. It looks a lot like the 1964 theorem. Instead of hidden variables now, he's letting lambda be beables in some general, very general sense. Could even be the wave function if you want to treat the wave function as some physical thing that really exists. A and B are far separate in measurement outcomes. He's more general now and allows them to take on any values bounded in absolute value by 1. Little a and little b are local measurement settings. And now he's going to let all of these things be beables also. He's not necessarily assuming these are abstract measurement interventions. Here are his new assumptions for local causality. He assumes there is a sufficiently rich collection of local beables lambda in the overlap of the past light cones of the measurement outcomes A and B, treated now as local beables themselves. He's assuming there's a rich enough set of local beables lambda in the overlap of their past light cones that the conditional probabilities for A, the measurement outcome of A, condition and everything else, and on lambda, you lose any dependence on the measurement settings little b and on the outcome B. Lambda screens them off. Similarly for B, when you plug lambda into the conditioning, you screen off any dependence on little a or big A. That's his assumption. Now, as a general statement about how joint and conditional probabilities work, we have the following identity. This is a basic identity that relates conditional probabilities. This is just automatically true for how conditional and joint probabilities work. And so you can take Bell's criterion and write it like this. The joint probabilities for A and B conditioned on the measurement settings and on lambda factorizes into conditional probabilities for A alone, depending on lambda, and for B alone, also depending on lambda. That factorization is crucial. That's the factorization that Bell needed. So he plugs that factorization in. He now gets a good factorization in his formula for expectation values, and he's able to derive a generalization of his inequality. So any measurement stochastic theory that satisfies Bell's local causality assumptions is going to be ruled out by experiment. Bell concluded that all other theories, including the textbook theory, therefore involve non-local causation. He argued that any empirically adequate theory equivalent to quantum mechanics, empirically makes the same predictions as quantum mechanics, violates this local causality assumption, and therefore is non-local. But Bell's new principle of local causality tucked in a new implicit assumption, as is manifest in its factorization form, and that's Reichenbach's principle of common causes. In modern form, Reichenbach's principle states that if A and B are variables that are correlated, their joint probabilities do not factorize, but A and B do not causally influence each other, then there is the assertion that there must exist, a positive active assertion, there must exist some other variable C, such that when you condition the joint probabilities on C, you get this factorization. Okay? In words, we have the assertion, Reichenbach's principle of common causes, that there must exist a common cause variable C that screens off the correlation. If A and B are correlated but not causally influencing each other, then there must exist a variable C with this property, a common cause variable C. Let's look back at Bell's principle of local causality, right? And here it is in its equivalent factorization form. This is clearly an application of Reichenbach's principle, even though Bell does not mention Reichenbach in any of his known published writings. So clearly these are an application of Reichenbach's principle of common causes. They are actively asserting the existence of particular causal influences. They're asserting that there must be a rich enough set of variables lambda in the overlap of the past light cone that play the role of the common cause. Essentially, Bell didn't have a concrete microphysical theory of causal influences, so he assumed that any causal local theory, even though he didn't have like a clearly written one, but any causal local theory should entail local Reichenbachian common cause variables. He assumed that this sort of factorization should be a feature of all such theories, and then he showed that it leads to the Bell inequalities, which are violated by experiment, and therefore you can't have a causal local theory. That's basically his argument. Reichenbach's principle of common causes may seem intuitively plausible, but that's far from an obvious reason to require it as a part of a condition on causal locality. For one thing, it assumes every common cause is a variable that you can plug into conditional probabilities, you can condition on, you can sum, integrate over. Bill Unruh noted this in 2002, and he wasn't the only person who noted this. But he says it's true that the common cause for like an EPR type setup cannot be stated in exactly the form for which Reichenbach set up to describe common causes for a classical statistical system. But that's not surprising, right? And in particular, those correlations don't arise mysteriously, somehow in the development of a widely spaced system. They don't require some mysterious non-local action to be explained. They're simply there as correlations in a classical system due to the evolution from a common cause in the past. Right? There was, in fact, a common cause, but it was just not a variable. Reichenbach's notion of common causes, which Bell implicitly used, was just too narrow a picture of what a common cause could be. The common cause is just an interaction between the two systems. They had to interact, become entangled. And that interaction is the common cause, but it's just not a Reichenbachian variable. It was too simple to assume that the common cause in this case is the kind of a thing that's a variable. Now, there have been other theorems over the years claiming to demonstrate non-local causation, EPR, GHZ. There's some more recent ones. They all make all kinds of assumptions that simply don't hold. And I should also point out that advocates of Everettian quantum theory already deny that the premises of any of these theorems capture the correct notion of locality. What I'm going to show now, and this is the final part of the talk, is that the new unistochastic formulation of quantum theory exploits the loopholes that I've laid out to allow, first, for an improved criterion for causal locality, to let us talk causally about quantum theory, and then with that notion of causal locality to show that quantum theory is causally local. The first step is to note a key connection with a completely different theory. In the theory of Bayesian networks, from the theory of causal modeling, one considers a set of random variables related by a collection of basic directed conditional probabilities. You see diagrams like this. This is a very simple Bayesian network. We've got 4 random variables, A, B, C, and D. This causal model supplies a basic directed conditional probability distribution. Probability of A taking on a particular value, little a, conditioned on the instantiated values for B, C, and D. Okay? We call B, C, and D exogenous variables, right? They sort of fluctuate, and their values depend, probabilistically on whatever concrete instantiation of the process we're considering. And then the endogenous variable A inherits a contingent probability distribution through these conditional probability distributions. In any concrete instantiation of this Bayesian network, again, one has contingent joint probability distributions for the exogenous variables B, C, and D, and then the laws, the arrows, induce a standalone probability distribution for the endogenous variable A. Now, one can go ahead and define other conditional probability distributions using Bayes' theorem, but these will not have the same status as this one, this brown one, the one that goes from B, C, and D to A, the one that was the arrows in this diagram, okay? You can introduce other conditional probabilities like P of B given A, C, and D, but if you do that, you're going to get these really complicated nonlinear formulas, and these formulas will depend nonlinearly on contingent instantiated probability distributions. They clearly do not have the same fundamental status as these brown conditional probabilities that are specified in the model. So the basic directed conditional probabilities, directed from B, C, and D to A, right, have a more fundamental status in the specification of this model than other conditional probabilities you'd write down. They have the status of the laws of the model. Right? Crucially, Bayesian networks have been a non-interventionist causal reading. If your causal model supplies a basic directed conditional probability distribution of the kind I just gave you, then any stochastic fluctuations in B, C, and D dictate stochastic fluctuations in A. Taking this seriously, one can argue that by supplying such laws, these directed conditional probabilities that are directed from B, C, and D to A, the model is asserting that B, C, and D are exerting causal influence on A. Right? And that's if you want to give it a causal reading. You don't have to, but arguably this is a hospitable domain for attaching causal language. Notice how the directedness of these conditional probabilities from B, C, and D to A nicely captures the asymmetric nature of cause and effect relationships, but without necessarily privileging an arrow of time. I didn't say who was first or which was first in time or second in time. This is causal asymmetry without necessarily relying on an asymmetry in time. So it threads a very fine needle. All right, so now we're basically done. The unit-stochastic formulation of quantum theory reviewed in this talk is based on microphysical laws consisting of directed conditional probabilities, just like for a Bayesian network. Those directed conditional probabilities in the Bayesian network are just like the microphysical conditional probabilities that I specified in these models. The unit-stochastic formulation therefore provides a hospitable domain for causal talk. One can arguably apply a causal reading to those directed conditional probabilities, and in that sense, one can regard quantum theory as a microphysical theory of causation par excellence. Consider now an overall unit-stochastic system consisting of two subsystems Q and R. Well, we've got two subsystems, so the overall system's microphysical conditional probabilities will take the following form. Our initial configurations are ordered pairs for the two systems. Final configurations are also ordered pairs for the configurations of the two systems. And now a definition. Subsystem Q will be said to be free of causal influences from subsystem R over the time interval from 0 to t, if after marginalizing over R, the resulting conditional probability distribution has no dependence on R left over. So if we're just interested in the conditional probabilities for Q alone, then any dependence on R goes away. That is going to be our statement of causal independence. Now I can state an improved principle of causal locality that I will argue improves upon Bell's principle of causal locality. A theory with microphysical directed conditional probabilities of the kind we've been talking about is causally local if any pair of localized systems Q and R that remain at space-like separation in the given experimental situation never exert causal influences on each other in the sense that the directed conditional probabilities for Q are causally independent of R and vice versa. Okay? Now it's just a straightforward calculation to show that with this definition, this principle is indeed satisfied. Okay? This is the simple calculation. Suppose Q and R are space-like separated. Textbook rules for what the unitary time evolution operator for the full system are give us this tensor product relationship. Tensor products commute with mod squaring, so the same tensor product holds at level of the stochastic probabilities. Well, by definition, that means the stochastic probabilities factorize, and then you can just marginalize and you get the answer. So it works out exactly perfectly. It's a very simple calculation. By contrast, suppose that Q and R are not kept at space-like separation. Suppose they do interact at some intermediate time t prime between 0 and t. Well, at that one time t prime, we do not get this tensor factorization of the unitary time evolution operator against standard quantum mechanics. And what that means is that at all times starting at t prime and later, we will fail to have factorization for the stochastic probabilities of the two systems. And that's because gamma of Q and R encodes cumulative statistical effects starting at 0, at least until the next division event. So once there's an interaction, the stochastic dynamics will fail to factorize forevermore, at least until there's some division event at some time later. This breakdown in the factorization of the dynamics starting at t prime is exactly entanglement, manifested now in the language, the level of the underlying indivisible unistochastic process. So now the two subsystems Q and R, they're exerting causal influences on each other, stemming from their local interaction at t prime. But that local interaction is not a Reichenbachian variable. Okay? So this is a concrete example of a theory with a causal language, causal notions, but does not entail Reichenbachian common cause variables. All right, adding the observer subsystems A for Alice and B to Bob to model the original EP argument doesn't change any of these basic facts. Here's the setup. Q and R original systems, they interact at some time t prime and they separate in space. They meet up with A for Alice, B for Bob, and then Alice and Bob do their measurements. Alice and Bob are assumed to remain at space-like separation throughout the experiment. You can just, by straightforward calculation, show that B, Bob, does not exert causal influence on A in exactly the required sense. That causal influence disappears. The only causal influences on A come from Q and R, which, after all, both interacted in the past light cone of A, just as expected. So in short, this is the short picture. Consider a stochastic process over a fixed orthogonal basis, but without imposing all the intricate nomological structure of a textbook stochastic process. and you get quantum theory. One then arrives at what appears to be a causally local hidden variables theory under the notion of causal locality that I've introduced, based on simpler axioms than textbook quantum theory, arguably without a measurement problem, no preferred role for measuring devices, and deflating a lot of the exotic talk about quantum phenomena. There are many prospects for interesting future research directions, applications to dynamical systems and stochastic processes, new algorithms for quantum simulations, new ways to think about quantum causal models, implications for many old problems in statistical mechanics. I'm particularly interested in that. We can talk about that in the Q&A. Ramifications for algebra first, like C-star algebra, von Neumann algebra approaches, maybe generalizations of quantum theory, because now we're starting with different axioms, and maybe new possibilities for quantum gravity. I want to conclude with the following quotation, highly relevant quotation from 1956. Nevertheless, there can be no fundamental objection to the idea of a stochastic theory except on grounds of a naked prejudice for determinism. Who wrote this? Any suggestions? Actually, I think you're muted, so you can't answer. Think about it for just a second. Who said this? Okay. This was Hugh Everett III in his unsubmitted, long-form PhD dissertation, The Theory of the Universal Wave Function, which first introduced the many-worlds interpretation. He was actually talking about Bopp's stochastic theory, the one from the 1940s. Just an interesting little note. All right, thank you.